Hello everyone, my name is Prashant from BSc Chemistry Honors first year, and today we are going to read Electrochemistry Part 2. D by Huckel Osenager equation for strong electrolytes, D by Huckel theory of strong electrolytes. Peter Debye and E. Huckel in 1923 put forward their theory of strong electrolytes. As the solution is diluted, its molar conductance increases. Arrhenius attributed this increase in the degree of ionization and used it as a method of calculating the degree of ionization of an electrolyte by the equation alpha is equal to lambda m by lambda node m. But according to the modern theory of strong electrolytes, the degree of ionization of strong electrolytes is unity even at moderate concentration. Therefore, the above relationship is not correct in the case of strong electrolytes. Debye and Huckel suggested that increase in molar conductance with dilution in the case of strong electrolytes is due to increase in the mobilities of ions due to weaker interionic attraction rather than to increase in degree of ionization. Similarly, decrease in molar conductance with increase in concentration is not due to fall in the degree of ionization but fall in the mobilities of ion due to greater interionic effect. As the concentration is increased further, the positively charged ions come closer all the more. The interionic forces therefore become still more appreciable than the ionic mobility falls further. Thus, according to this theory, in case of strong electrolytes, interionic attraction and not partial dissociation is the cause of decrease of conductance with increase in concentration. According to this theory, each ion in solution is surrounded by an ionic atmosphere consisting of other ions whose net average charge is opposite to that of central ion. This ionic atmosphere is spherical and symmetrical in nature in the absence of any potential. However, when potential is applied, the ions start moving towards the respective electrodes, and as the result, ionic atmosphere is distorted, which results in the decrease in same speeds of the ions. Debye and Huckel showed that these effects are due to two factors. First, relaxation or asymmetric effect. Second, the electrophoretic effect. A. Relaxation or asymmetric effect. In figure, the central ion is positively charged and is surrounded by an atmosphere of negatively charged ions. When an electric field is applied, the ions are set in motion. The central ion move in one direction and the atmosphere in opposite direction. Positive ions move towards cathode and negative ions move towards anode. The symmetry of the atmosphere about the ions is destroyed and atmosphere becomes destroyed. Consequently, the force exerted by the atmosphere on the central atom is no longer uniform in all directions. It is greater behind an ion than in front of it. Thus, the central ion experiences a retarding force opposite to the direction of its motion, with the result that its speed is lowered. Electrophoretic effect. The solvent molecules attached to ionic atmosphere move in direction opposite to that of central ion. Thus, they cause friction due to which the, the mobility of central ion is retarded. Effect is called electrophoretic effect. The third factor which affects the mobility of ion is the viscous effect. Viscous effect is inversely proportional to mobility of ions. In 1926, Debye and Huckel and Osenager worked out mathematically the magnitudes of asymmetry and electrophoretic effect in terms of such factors as valency of the ions, ionic concentration, and dielectric constant and viscosity of the medium. For univalent electrolytes such as KCl, which furnish two univalent ions, the following equation was delivered. Lambda m is equal to lambda node m minus bracket 82.4 by ERT whole power 1 by 2 eta plus 8.20 into 10 raised to power 5 by ERT whole power 1 by 2 lambda m bracket closed root c, where Er is dielectric constant, eta is coefficient of viscosity of the medium, T is absolute temperature, C is concentration of the solution in moles per liter. Equation 2 is known as D by Huckel-Osenager equation. As is evident. Lambda m is less than lambda node m. This is partly due to electrophoretic effect and partly due to asymmetry effect. The first term in the bracket gives a measure of electrophoretic effect, while second term gives a measure of the asymmetry effect. For a given solvent and at given temperature, equation 2 may be expressed as lambda m is equal to lambda node m minus a plus b lambda m root c, where a and b are the Debye-Hückel constant. A is equal to 82.4 by E R T whole power 1 by 2 and b is equal to 8.20 into 10 raised to 5 whole by ERT whole power 1 by 2. The values of A and B for water at 25 degrees Celsius comes out to be 60.2 and 0.229 respectively. If the equation is correct, then by plotting lambda m against root c, a straight line of slope is equal to bracket 60.2 plus 0.229 lambda node m should be obtained. If a solution is at infinite dilution, if c is almost 0, then the second term on the right hand side of the equation becomes negligible and lambda m approaches lambda node m as expected. Uses of Ostwald dilution law. Calculation of dissociation constant of a weak electrolyte. K is equal to lambda square m alpha square m by 1 minus alpha v, where alpha is equal to lambda m by lambda node m. Calculation of relative strength of two weak acids or weak bases. For any weak acid or weak base at dilution V, K1 is equal to alpha square 1 by 1 minus alpha 1 V. Similarly, for other weak acid or weak base at dilution V, K2 is equal to alpha square 2 by 1 by minus alpha 2V. In case of weak electrolytes, 1 minus alpha is almost equal to 1, hence equation 1 and 2 can be written as K1 is equal to alpha 1 square by V, K2 is equal to alpha square 2 by V. Divide equation 3 by 4, then we get alpha 1 by alpha 2 is equal to root K1 by K2. Thus relative strength of weak acid or weak base is equal to the square root of ratio of equilibrium constants. Calculation of pH of a solution. We know that K is equal to alpha square by 1 minus alpha V. For weak electrolytes, 1 minus alpha is almost equal to 1. K is equal to alpha square by V, or alpha square is equal to KV. Alpha is equal to root KV. Concentration of H positive is equal to alpha by V, or H positive concentration of H positive is equal to root Kc. Therefore C is equal to 1 by V, but pH is equal to negative logarithm of concentration of H positive, or pH is equal to minus log root Kc. Applications of conductivity measurements. Determination of degree of dissociation, determination of Ka of acid, determination of solubility product of sparing soluble salt, conductometric titrations. Determination of degree of dissociation. The degree of dissociation of a weak electrolyte at any dilution can be calculated by relationship alpha is equal to lambda m by lambda node m. Lambda m is equal to molar conductance, lambda node m molar conductance at infinite dilution. Determination of Ka of acids. The dissociation constant of acid Ka can be determined by following expression. K is equal to C alpha square by 1 minus alpha, or Ka is equal to alpha square by 1 minus alpha V. Alpha is equal to degree of dissociation, C is equal to concentration, V is equal to diluted volume. Determination of solubility product of sparing soluble salt. There are a number of salts such as silver chloride, barium sulfate, lead sulfate, etc., which are so sparing soluble in water that their solubilities cannot be determined by any chemical method. These are generally regarded as insoluble. However, it is possible to determine even such extremely small solubilities by conductance measurements. Solubility of a sparing soluble salt is equal to S is equal to 1000 into E into K by lambda positive node plus lambda node negative gram per liter. where E is equal to equivalent weight of salt, K is equal to specific conductance, lambda node M is equal to molar conductance at infinite dilution. Relationship between solubility and solubility product. Ksp is equal to this equation here written. Applications of conductivity measurements. Determination of degree of dissociation, determination of Ka of acid, determination of solubility product of sparing soluble salt, conductometric titration. Fourth, conductometric titration. The determination of the end point of titration by means of conducting measurement is termed as conductometric titration. The principle involved is that electrical conductance depends upon the number of mobility of ions. Example: 1. Titration of strong acid HCl with strong base NaOH. The acid is taken in conductivity vessel and the alkali in burette. The conductance of HCl is due to the presence of hydrogen and chloride ions, and alkali is added gradually. The hydrogen ions are replaced by slow moving sodium ion. H positive aqueous plus Cl negative aqueous plus Na positive aqueous plus OH negative aqueous gives Na positive aqueous plus Cl negative aqueous plus H2O liquid. On continued addition of sodium hydroxide, the conductance will go on decreasing until acid has been completely neutralized. Any subsequent addition of alkali will result in introducing fast moving hydroxyl ions. The conductance therefore, after reaching a certain minimum value, begin to increase. On plotting the conductance against the volume of alkali added, the points will lie on two straight lines CD and CD. The point of intersection of X of these two lines gives the volume of alkali required for the neutralization. Second, titration of weak acid CH3COH with strong base NaOH. The conductance of acid will be low due to its poor dissociation. On adding the base highly ionized sodium acetate is formed and hence the conductance begins to increase. CH3COH aqueous plus NaOH aqueous plus OH negative aqueous gives CH3COO negative aqueous plus Na positive aqueous plus H2O liquid. When the acid is completely neutralized, further addition of base introduces excess of fast moving hydroxyls ion. The conductance of solution therefore begins to increase even more sharply than before. On plotting the conductance against volume of the alkali added, the two lines obtained the point of intersection into gives x gives the endpoint. Third, titration of sorry. Third, titration of mixture of strong acid HCl and weak acid CH3COH with strong base NaOH. HCl being a much stronger acid will get titrated first. The titration of acetic acid will commence only after HCl has been completely neutralized. A combination of curves 1 and 2 is obtained. Point B responds to neutralization of HCl and point C corresponds to neutralization of CH3COH. Fourth, titration of strong acid HCl with weak base NH4OH. The conductance will fall at first due to the replacement of fast moving H positive ions by slow moving NH4 positive ions. H positive aqueous plus Cl negative aqueous plus NH4OH gives NH4 positive aqueous plus Cl negative aqueous plus H2O liquid. After neutralization of the acid, further addition of weakly ionized ammonium hydroxide will not cause any appreciable changes in the conductance. Advantages of conductometric titration. They are particularly useful in the case of colored or turbid liquids where ordinary indicators cannot function. The method is also helpful in case of very diluted solution and also for weak acids and bases. No special care is necessary near the end point of it is determined graphically. Thank you.